All right, hi class, welcome back. So we're going to jump into section 7.4. In this section, we're going to introduce partial derivatives. And so we're going to define them, and we're going to work some examples on how to solve for them. And then we're also going to use partial derivatives to answer questions about real life situations and be able to solve them. And then use this also define higher order partial derivatives. All right, so let's jump into a quick introduction. Now that we have some familiarity with the functions of two variables, it is time to start applying calculus to help us solve problems with them. So in chapter 2, back then, we learned how to find the derivatives of one variable functions. So now that we know that derivatives tell us about the shape of the function, and that tell us where we can find the local max and local min. We want to be able to do the same thing for functions of two variables. So let's first think about and imagine a surface, for example, a mountain, and it's a three-dimensional. So if you think about it at this mountain, you can actually move into different directions, right? Or actually at least two different directions. You can say you can move into the north side or the south side or the left side, east side or west side, right? But this actually has more than those directions, right? We can think about that. We can actually move in different directions from the top of the hill. But let's just focus on two directions. And then so if we look at the top of the hill from the top part of the function from a bird eye, we can see that we can easily move from up and down and from the top of the hill, right? So imagine the surface is smooth and has some hills and some valleys. Concentrate on one point on your surface. What do we want for the derivative to tell us? It should tell us how quickly the height of the surface changes as we move. So wait, which direction do we want to move? So this is the reason the derivatives are more complicated for functions of several variables. There are so many directions we can move from one point. So it turns out that our idea of fixing one variable and watching what happens to the function as other changes are the key to extending the idea of derivatives to more than one variable. So let's jump in to define what is a partial derivative. All right, so partial derivatives. So let's suppose you have a function z defined as f of x of y, which is a function of two variables. So the partial derivative of f with respect to x is the derivative of the function f of xy, where we think of x as the only variable and act as if y is a constant, right? So we're going to treat y as a constant and x as the variable. But if we're taking the partial derivative of f with respect to y, it is going to be the derivative of the function of f, xy, where we think of y as the only variable and act as if, where x is a constant, right? So we're going to think about x as a constant and y as the variable. So when we're doing the partial derivative of f with respect to y, we're treating y as a function. So with respect to x or with respect to y, part is really important, right? So the part is really important. So you have to know you have to know and tell which variable you're thinking as the variable. So it's important for us to know and it be clear when they're asking us to compute the partial derivative. And how this applies geometrically. So geometrically, the partial derivative with respect to x gives us the actual slope of the curve, as like it did it before. As you travel along the cross section, a curve of the surface parallel to the x-axis, the partial derivative with respect to y gives us the slope of the cross section parallel to y-axis. So tell us how is the function changing in respect to the y-axis, right? If you're moving along in the direction of y, then you are going to be able to find how the function is changing. All right, so what notation are we going to be using here? Right, so what notation are we going to use? So if the partial derivative of z equals f of xy, then what we're gonna with respect to x, then it's gonna be written as f partial derivative with respect to x of xyz. So if you notice here, we have this little symbol that is different that we haven't seen before. It is a subscript, right? And so this means it's a partial derivative with respect to x of the function fx of y. So that means we're going to treat x as a variable and y as a constant. Also, we can rewrite it as f partial derivative with respect to x. Or we can say, since z is also equal to the function, we can say the z partial derivative with respect to x. All right, so these are some notations, but we can also write it with the Leibniz famous notation. And that is we're taking the partial. We notice that this is a symbol that we haven't seen before. And this means it's a partial derivative of f with respect to x. And it's written like a backwards 6, right? If you think about 6, then you write it backwards, right? Or we can say that the partial derivative of z with respect to x. So as we mentioned before, it's very important that we know with what respect this partial is being taken off, right? And if you think about it, the function will have multiple variables, and so it's very important for us to know which is the derivative in respect to, and which one is going to be treated as a constant. And as you guys can see here, it's very similar to what we've done before, right? So let's use an adaptation of the partial derivative of z with respect to x notation, which means the partial derivative of f of x y with respect to x. The partial derivative of f of x y with respect to x. And you can see here that we're taking the partial derivative of the function with respect to x. And we can also write it like this, right? So how do we compute it, right? So to compute the partial derivative from a formula, right? If f of x, y is given as a formula, then you can find the partial derivative with respect to x algebraically by taking the ordinary derivative, thinking of x as the only variable, and holding y as a fixed constant, right? As a fixed constant. So of course, everything here works the same way if we're trying to find the partial derivative with respect to y. Just think about y as your only variable and act as if x is a constant. So the idea of the partial derivative works perfectly well for a function of several variables. You focus one variable to be the variable and act if the other variables are constants, right? And that's it, right? So we got to do one term at a time. All right, so we're gonna jump into the example in the next video. So I hope you guys found this helpful. Please let me know if you have any questions. I'll see you guys next time. Thank you. Bye-bye.